Today we are going to talk about a linear algebra question which was asked in the Engineering Sciences GATE 2023. So question was that consider there are matrices P and Q of sizes 3 by 3. The eigenvalues of both P and Q are given 1, 1 and 2. Which one of the following statements are true? Both P and Q are diagonalizable. P is diagonalizable but Q is not diagonalizable. P is not diagonalizable but Q is diagonalizable. Both P and Q are diagonalizable. So now, in order to understand this, first we note that the eigenvalues are given for P and Q, and it is clear that if you have a square matrix of size n, then it should have n eigenvalues. So we are given a 3 by 3 matrix P and 3 eigenvalues. Similarly, 3 by 3 matrix Q and 3 eigenvalues. So clearly all the eigenvalues of P and Q are known. Okay? So we do not need to further calculate any eigenvalue. Eigenvalues of matrices are given, and they are given same, that both these matrices have the same eigenvalues, which is given 1, 1 and 2. Okay. Now the question is based on diagonalization, and we know that a matrix will be diagonalizable if it will have n linearly independent eigenvectors. So for example, if you have 3 by 3 matrix P, then it should have 3 linearly independent eigenvectors. Similarly, Q will be diagonalizable if we have 3 linearly independent eigenvectors. Now there is a eigenvalue 2 which is distinct, non-repeative, and we know that if we have a independent distinct eigenvalue, then it will always give a eigenvector. Okay, so we already know that this eigenvalue will be linked with one eigenvector for both P matrix and Q matrix. For P matrix we will get one eigenvector, and say for Q matrix we get another eigenvector, but still we will have one eigenvector. The value 1 is repeated eigenvalue, and against a repeated eigenvalue we may have one eigenvector or two eigenvectors. Okay, so for P to be diagonalizable we need three eigenvectors. One is already given by this 2 value. For the 1, 1 value we need to check whether it will give two eigenvectors or one eigenvector. Similarly, for Q matrix also we need to check for this repeated eigenvalue whether it will give one eigenvector or two eigenvectors. So if we get two eigenvectors against this value of 1, then we will have the corresponding matrix as diagonalizable. If we will not get the two eigenvectors against this eigenvalue, then it will not be diagonalizable. So let us say check for the P matrix. So if the eigenvalue lambda is 1, to calculate the corresponding eigenvectors, we need to solve the homogeneous equation. For the P matrix, it will be P minus lambda I times x vector equal to 0. And because lambda is 1, so we only need to solve actually is the P minus identity times x vector equal to 0. So it's a homogeneous system. So if we write the augmented matrix for homogeneous system, clearly P minus identity, that means that every element in the diagonal will be subtracted by 1, so that this matrix can be written as 3 minus 2, 2, 6 minus 3 minus 1 will be minus 4, 4, 3 minus 2, and 3 minus 1 is 2, and the right hand side is a 0 vector, so 0, 0, 0. Okay. So clearly this is P minus I equal to 0, and you can easily see that if I apply the elementary operations to reduce it with this as the first pivot position, if I apply and try to reduce it to equivalent form, then I can apply row 2 minus 2 times row 1, and similarly row 3 minus row 1, and immediately you see we'll have this 3 minus 2, 2, 0. All elements here will become 0. So clearly what we are getting is one pivot position, and these two columns are free columns. And we know that if we have two free columns, then we are going to get two eigenvectors against this homogeneous system. So clearly P matrix, for this eigenvalue 1, we will get two eigenvectors, and already one eigenvector is there for eigenvalue 2. So total we are going to get three eigenvectors for this P matrix, and so P is diagonalizable. Okay. So clearly this says that P is diagonalizable. Similarly, we can check for the Q. Again, if I use lambda value as 1, and for the Q matrix I need to solve then Q minus identity of x times 0. Okay. With lambda value 1 it becomes Q minus x I. So if I write the augmented matrix, then again I have to subtract the diagonal elements of Q with 1. Okay. So this element, it will become 2, this will be minus 4 minus 1, that's minus 5, and 5 minus 1 will be 4. Okay. So what we will have here is 2 minus 2, 2, right hand side will be 0 vector because of the 0 vector here. Okay. And second row will be 4 minus 5, 6, 0, and third row will be 2 minus 3, 5 minus 1, 4, 0. Okay. So again if I apply elementary row operations, I know this is my first pivot position, so I will try to eliminate these two elements. So row 2 minus 2 times row 1. Okay. Row 1 remains the same, 2 minus 2, 2, 0, 4 minus 4, 0, minus 5 plus 4 will be minus 1, and 6 minus 4 will be 2, 0. Third row minus first row, so 2 minus 2 is 0. So minus 3 plus 2 is minus 1, and 4 minus 2 is 2, 0. Again, so this is my first pivot, and then if I take this as second pivot, clearly second row first non-zero element, I eliminate this. So clearly what I can see is that I will get first row 2 minus 2, 2, 0, 0 minus 1, 2, 0, and third row will become 0, 0, 0, 0 if I apply row 3 minus row 2 and impact on row 3. So clearly I have two pivot positions and only one free column. Okay, so one free column, that means I am going to get one eigenvector against this eigenvalue lambda is equal to 1. So total eigenvectors that I am going to get is 2, because one I have from this eigenvalue 2 and other 1 from lambda is equal to 1. So since I am not getting the three eigenvectors against these eigenvalues, so clearly the matrix Q, this matrix is not diagonalizable. So clearly you can see that the option B is correct in this case. Okay. The P is diagonalizable, but Q is not diagonalizable. Okay. So again, the matrix will be diagonalizable if it has the n number of linearly independent eigenvectors if we are working with a n by n matrix. So for a 3 by 3 matrix we should have 3 linearly independent eigenvectors, okay, which is true for P but not for Q in this case. If you would like to know more about the process that we have used, so you can uh, go through the linear algebra lectures and see the lecture for eigenvalues and vectors, and also the lecture for diagonalization. Thank you.